Properties of vectors. I've written out, well, I've copied the properties of vectors from something we have here. And it just talks about the different names of them, and they are essentially really rules that have to do with our adding and multiplication rules. Okay? Cumulative property really states that if you can add two numbers one way, you can add them in reverse and still get the same answer. The idea being something like 5 plus 3 is 8, and 3 plus 5 is also 8. It doesn't make a difference. And I'll just prove it with our vector combinations after. That same idea goes with, say we're adding three things, associative property. Whatever we add first, if doing addition, we can add the other two and add the first part last and still get the same answer. So let's say we had 5, 3, and 2. That's going to give us 10. Or we have 5, 3, and 2. We do these two is 5. 5 plus 5 is 10 again. Exact same idea. Distributive property states that we can distribute our k value to each of the values within a bracket, and our answer is the equivalent of just multiplying that number by each of the vectors. Okay? Adding a 0 vector, okay, to a vector just gives us whatever our vector is. There's no magnitude to that vector or directions, so we're just left with what we started with. And for scalars, same idea with multiplication. Whether we multiply the vector times the scalar first and then the outside scalar, or we multiply the two scalars and then the vector, we still end up at the same answer. And this is the same as the original distributive law. So we'll try to show that with vectors so these things make sense. Okay, the very first one said that if we add a plus b, oh, wrong button. So if I take a and I add b to it, okay, and we've already done this before. Here's a and b. We know that our resultant vector is going to be this. What they're saying is it doesn't matter if we do a first and then b. So with that being said, let's do b first and then add a. And boom, we're at the exact same resultant vector. We've already done that idea before. That makes sense. With the associative law, the idea is that if we add AB first and then C, or if we add BC first and then A, we should end up with the same vector combination. So let's try that idea. If we take our A, then our B, okay, so this is the order of A, B, and then C. Our resultant vector is right there. So that's our A plus B plus C. And what it's stating is that we can do BC first. So let's try that. B, C. I'm going to have to extend the page a little. And then A. And our resultant vector is the same. So it didn't matter what order we put these in. We decided to do B, then C, and then A, and we still ended up with the same resultant vector. Okay, so it doesn't matter the addition order. As long as we just add them all properly, we end up with the same resultant vector. So the first two. The last one has to do with the scalar. So I'm going to copy these and put them on another page just so we have some room. Oh, I don't think I can do that. Okay, never mind. I'm just going to bring them down. Let's say we had a scalar of something like this. They've given us 2 vector A plus vector B. Okay? According to this rule, our distributive property rule, we should be able to just bring the 2 into each of the vectors, and the equivalent idea would be 2 times vector A plus 2 times vector B. Okay? In other words, our resultant vector to these two should be the equivalent of this. So with that idea, think of it like this. If we have vector A, which I'm going to have to scroll up and, well, maybe if I just make these. Oh, that's a good idea. Let's just do that. Okay, so we had our original vector A and our vector B. Okay. We know that what this is essentially saying is our resultant vector here of A and B we can just multiply this resultant vector times the value of 2. So this being our vector A plus vector B. This is our resultant vector. If we multiply it by 2, it would be the same as taking the scalar of A twice and the scalar of B twice. You'd have the exact same vector idea. So let's try that idea out. What it's saying now is I'm going to take A and B twice, put them together twice, and see if it's the same as doubling this vector here. So we take A, hopefully it'll fit, 1, 2, okay? And then we take 2 of B. Oh, fit on the page, please. 1, 2. Okay, so in this case, this is 2A, and this is 2B. Our resultant vector should be just double this original resultant vector we got. So we take 1 and 2. Hopefully I lined them up well. There we go. Okay, and it works out perfectly fine. That idea of 2A plus 2B. Okay, so that's essentially a distributive property. It ends up giving you the exact same things. That's what it means when we do this. Oh, okay, better keep that in mind. Associative rule, if we add 0 to a vector, I have vector C here. Right? So let's take it. Vector C plus the vector of 0 gives us vector C. I have the vector. I don't add anything to it. Got the same vector. Didn't do anything. That's pretty easy to prove. Okay? Associative laws for scalars is essentially just remembering that we can multiply our values in either order. Okay? We've already talked about how the distributive law, this is essentially distributive law backwards. So we've already just talked about that. That's the distributive property. And this is an associative property. So instead of showing you with vectors, we're just going to simplify some vector expressions. Okay? So some vector expressions they may give you. Let's say they give us something like vector x is equal to, let's say, 2I plus 3j minus 2k. And those will make sense to us later on. Vector y is negative 2I minus 6j plus k. Okay. Yeah, this is a good one we can use. They might ask us in a question to take 2y minus 3x. Okay? And that idea is we can, and this is very similar to substitution. I know there's a lot of vectors involved here, but think of the idea of this is vector x. Okay? I can replace vector x with all of these 3 vectors. So I'm going to replace vector x with those 3 vectors, and we'll just have a scalar of 3 on the outside, which I'll need to apply to all of these. Okay? And same with our y. So we're going to do that for both of these here. We have 2, and we're going to replace the value of y with these 3 vectors here. So we have negative 2 vector I minus 6 vector j plus k. Okay, minus, and let's do our x here. We'll replace x with these values. 2I plus 3j minus 2k. Okay. So what these rules are saying, this is kind of an all-encompassing question, is we just need to distribute and collect like terms. So I'm going to distribute this 2 value to all of the values inside the brackets and the negative 3. Very similar to much earlier math we've done. Okay, so 2 times negative 2 is going to give negative 4I, negative 12 vector j. These are vectors, so I have to keep the arrow on top. Plus 2 vector k. And the negative 3 gives us negative 6 vector I, minus 9 vector j, plus 6 vector k. So now that I have those, I'm just going to collect my like terms. These are my 2 I vectors. These are my 2 j vectors. And these are my 2 k vectors. So we put them all together. Negative 4 and negative 6 is the idea of negative 10 vector I. Negative 12 and negative 9 is negative 21 vector j. And 2 and 6 is positive 8 vector k. So this is an equivalent vector. What did I write as? 2y minus 3x. This is the equivalent of 2 vector y minus 3 vector x. These two are equal. Okay? I've just shown it in a different way. And this is the idea of using algebraically all those distributive properties that we just proved on the other page. Oops. Okay, these are the distributive properties, and this is our proof of them all using geometry. Okay? We just have to make sure we remember our associative and distributive